it's something that just sounds impossible at first, but then as we go on, we will build upon really easy and simple ideas, but at some point we will get to something that sounded impossible at the beginning. Okay, so before we talk about zero knowledge proofs, I have to give you a refresher on what proofs were, and especially I have to talk a little bit about NP. So I hope you've already passed some courses on complexity theory, but just in case, I'm going to give you a definition of the class NP. So we say that a problem is in NP. Problem, let's call our problem, I don't know, small p, is in NP if it satisfies the following conditions. So remember, the definition of NP was not that I can solve my problem in polynomial time. Actually, let me call my problem L, since I'm thinking of it as a language. So the definition of NP was not that I can solve my problem in polynomial time, but that if I'm given a solution to the problem and a proof for that solution, then I can check that proof in polynomial time. Okay, so imagine that this L is a decision problem. So it's a problem where you give it an input and it gives you either yes or no, 0 or 1. So I say that it is in NP if there exists an algorithm, and by an algorithm, of course, in a very formal sense, I mean a Turing machine, but you can just think of it as any kind of algorithm or a program, such that it does the following things. So I'm going to call this algorithm V, and these are the conditions that we needed. The first condition was that if I give an instance of this problem that is a yes instance, there should be a proof that it's a yes instance. And it should be possible to check this proof in polynomial time. So this is the way I would write it. I would say for every input X that is in my language L. So for every input that satisfies the conditions of my problem, every input whose answer is yes, there should exist some proof, and I'm going to call that proof Y, and this Y is in sigma star, such that if I give the input and this proof to this algorithm, it will tell me that this is a correct proof, such that if I run V of XY, the answer is 1. So basically, I think of this algorithm V as a verifier. It's a verifier in the sense that whenever I give it an input to the problem whose answer is yes, and I give it a proof, this verifier can check that the proof is correct. Okay. And then the second condition I wanted to have is that if I have some input that is not in my language L, so if I have an input to my problem whose answer is no, then there should be no such proof. So there exists no Y such that if I tell my verifier that this Y is a proof, my verifier would accept. Or another way of writing this is, of course, to say that for every Y, my verifier rejects. Okay. Now, of course, other than this, this is just the definition of a verifier at this point. In order for it to be in NP, I had to have this last condition that said basically these things should happen in polynomial time. So such that there exist, let's call it something like this, such that there exist polynomials P1 and P2. And then I say the length of my proof has to be P1 of X. And then I want to also have a condition that the runtime of my algorithm, so if I run my verifier on X and Y, the runtime is at most P2 of X plus Y. And here I mean the length of X plus the length of Y. So basically the definition of NP was that a problem L is in NP if I have a verifier for L. If I have an algorithm V such that when I give V an instance of my problem L, and I give it also a proof Y that says that this instance is really a yes instance, then this verifier can, in polynomial time, check if the proof is correct or not. So the role of the verifier is to check the proofs. And that's a fundamental idea in complexity theory, and it's fundamental in the definition of NP. Okay. But what I want you to see here is that in order to prove something, we are constantly disclosing it. So let's just do a very simple example. Let's say that I make a claim, and let's say my claim is this. My claim is that I know, let's say, the prime factorization of a really large number. Prime factorization of n. Okay, so let's say that there is a really large number n, and let's say we both know the number n, it's a shared value, and I'm just claiming to you that I know how to factorize this particular n. Now, how can I prove it to you? How can I prove to you that I really know the prime factorization of n? And let's say that we both also know that n is the product of two large prime numbers. Okay, so we know that n is p times q, but p and q are private. These are numbers that only I know, but you also know n. And I want to prove to you that I actually know a p and a q such that if I multiply them, I will get n. Now, of course, a very simple proof would be if I just give you p and q. So the simplest proof is disclose p and q. And so in this case, I'm the prover. I want to prove this, so I just give you p and q, and you're the verifier. You want to verify that this actually works, and the way you verify this, so verification, is that you just compute p times q and check if it's n. Okay, so very simple idea. We have two different people. I'm the prover, you're the verifier. I want to prove to you that I know something. And assuming that the thing that I want to prove to you is that I know the solution to some problem in NP, then I can just give you the solution and then you can just check it, because every problem in NP has a verification algorithm. And of course, this problem is in NP. So if I claim to you that I know the prime factorization of a number n, I can just give you the prime factorization, and it's easy for you when I give you the proof to check the proof. Now, crucially, it's not the same as finding the proof. Checking the proof is actually much easier, right? So if you don't know the prime factorization, it's actually quite hard to find it. But if you know the prime factorization, it's easy to prove it, because you can just give it to someone else and then they can easily verify it. So there is this distinction between verifying and actually finding a proof. Okay. But now the problem I have, and the main topic of this session, is that I want to prove something to you, but I don't want to disclose any information. And this is what we call a zero knowledge proof. So this is my problem. So let's say, again, we have two different people. We have a prover and a verifier. The prover wants to prove something to the verifier. So wants to prove some statement, some mathematical statement. Let's call it phi. to the verifier. But the really important point for the prover is that they want to make sure the verifier doesn't get any extra information. Now, since we always give names to people, the prover is usually called Peggy, and the verifier is usually called Victor. So Peggy wants to prove some statement phi to Victor, but she doesn't want to give any extra information. But she does not want to leak any information. Okay. So what do I mean by this? I mean that I want to have a protocol where Peggy and Victor actually interact with each other. And then at the end of this protocol, Victor should be convinced about the statement phi. And now this statement phi can be anything, but we're usually going to focus on proofs of knowledge. So usually in this course, when I say I want to prove something, I want to prove that I know something. Okay. So for example, here, Peggy wants to prove that she knows the prime factorization of n. But she wants this information to be the only information that Victor gains from the whole protocol. So at the end of the protocol, Victor should know that Peggy knows the prime factorization of n, but he shouldn't get any extra information. He shouldn't get P and Q. He shouldn't also get any other type of information. Okay? So that's why we call it zero knowledge. The only thing that is added to Victor's knowledge is the fact that this statement phi holds. It's the fact that Peggy knows P times Q. Okay. So before formalizing this, let me actually give you an example. And this is actually an example that people use all the time. So imagine that my verifier Victor is colorblind. Okay, so imagine Victor is colorblind. And let's say that we also have two balls, one is green and one is red, and Victor cannot tell the difference. Okay. So we have two identical balls. And these balls, one of them is green, one of them is red. Victor is colorblind, so Victor cannot tell the difference between these two balls. But let's say that Peggy is not colorblind. And so suppose that Peggy wants to prove to Victor that she can distinguish between these two balls. Okay? But I don't want to give any extra information to Victor. So an easy way of doing this, if I could give extra information to Victor, was to just tell him, hey, this one is green and this one is red, and then maybe have some way of proving it to him. But the problem I have here is that I don't want to give this extra information. So let me first start with a non-solution. Here's something that we cannot accept. So let's say that Victor takes the balls behind his back so that Peggy cannot see it. And each time he just randomly shows one of the balls to Peggy. Okay, so Victor shows a randomly chosen ball to Peggy. And then Peggy has to say the color. Now, if I do this as Peggy, I can actually prove to Victor that I can see color, right? I can prove with very high probability. because Victor will just take these balls behind his back, and every time he randomly shows one of the balls to me. And he can keep track of whether I'm actually changing the color or not. So if in his mind, he adds numbers to the balls, he has ball number 1 and ball number 2. Every time he's randomly showing one of them to Peggy. And if Peggy always says that ball number 1 is green and ball number 2 is red, then Victor knows that Peggy has a way of really distinguishing these two. Right? So I can prove to Victor as Peggy that I can actually see color. But the problem here is that I'm also leaking some information. It's not just telling Victor that I can see color, it's also telling Victor what color each one of these balls are. Okay? So, yeah, someone in the chat is saying machine learning. Well, now this is a problem. I don't want to do this. I want to somehow convince Victor that I can see color, but I want to do it so that he cannot figure out which ball is which color. And generally, I don't want him to gain any kind of extra information. The only information that Victor is allowed to gain is that Peggy can distinguish between these two balls. Okay, so here's a solution that we can have. And this is actually very similar to the previous one, except that it doesn't leak the color. So I can say that Victor, again, takes the balls behind his back, and every time he randomly chooses one of the balls and shows it to Peggy, and then Peggy has to say whether this is the same ball that she saw last time or whether Victor has swapped the balls. Okay, so at each step, Victor randomly shows one of the balls. And Peggy has to say whether the ball was swapped. Okay. Now, again, look at this from the point of view of Victor. If Peggy can always do this correctly, then you would be convinced with very high probability that she can actually see color. Right? Because you take the balls behind your back, you randomly bring one of them out, and if the balls were really the same, if Peggy had no way of distinguishing them, then Peggy would only have a 50% probability of answering correctly. Right? So if you just try this n times, the probability that Peggy can answer correctly every time is going to be 1/2 to the power of n, which becomes really small, really fast. So if she actually can do it all the time, you would be convinced after a number of tries that, okay, she can actually see color. But this doesn't leak any extra information, right? So Victor doesn't know anything extra here. Victor doesn't know the colors. Victor doesn't know anything other than the fact that Peggy can somehow distinguish these two balls. Okay, so this is what we call a zero knowledge proof. Let me give you another example. So this is also a classical example that people always use for zero knowledge proofs. This is the example of a cave. I'm really bad at drawing, so let's see if I can draw this. So let's say we have a cave that looks like this. Okay. And let's say there is a door here, and this door has a password. You can only pass through this door if you know the password. Okay. And again, here we are at a situation where we have a prover Peggy and a verifier Victor, and Peggy wants to prove that she knows the password. Now, again, a very simple solution here would be to just give the password to Victor, and then Victor can go inside this cave and pass through this door here, and he can verify that the password worked. But of course, the problem is that this solution is leaking the password, and we don't want that to happen. Okay, so my first non-solution is to disclose the password. Okay. But how can I have a zero knowledge proof? I want to somehow prove to Victor that I know the password without actually giving him any extra information. Okay. So here's the protocol that we can have. So let's actually give a real solution here. So in step 1, Peggy enters the cave, and let's actually give these two entrances 2 different names. So let's say this is entrance A and this is entrance B. So in step 1, Peggy enters the cave, and she gets to choose which entrance she uses, and Victor doesn't see which entrance she took. So the way this works is that she just goes in, takes one of these entrances, and Victor stands far away here. So Victor can see that Peggy went in, but Victor cannot see which entrance Peggy took. Okay, so Peggy enters the cave, choosing either A or B. And this is not visible to Victor. And then in the next step, Victor just shouts either A or B. So in step 2, Victor chooses A or B, and let's say that he chooses randomly, uniformly at random, and basically shouts either A or B. And then finally, Peggy has to come out of the entrance that Victor shouted. Okay, so again, if you look at this protocol, and this is basically the way we explain zero knowledge proofs to kids. Peggy has entered through either A or B, and Victor doesn't know which one, but Victor is choosing A or B randomly. So Victor is randomly asking Peggy to come out of A or B. So if Victor is choosing randomly, there is a 50% chance that he's going to choose the same entrance that Peggy took when she went in. And in that case, she can successfully come back out. But there is also a 50% chance that he chooses the other entrance, and then Peggy can only come out of the other entrance if she knows the password and she can pass through this door. So if we just repeat this, Peggy's probability of success in every iteration is 50%. So if I repeat this 100 times and Peggy can actually do it every time, the probability that she just got lucky every time is insanely low. It's 1/2 to the power of 100. So Victor can be convinced with very high probability that Peggy actually knows the password here and can actually go through this cave. Now, again, the really important property is that Victor doesn't learn anything other than this fact. The only thing that Victor knows, the only thing that is added to Victor's knowledge is that Peggy knows this password. Victor doesn't know anything about this password. Victor doesn't know how Peggy is doing this. The only thing that he knows is that Peggy somehow knows this password. Okay. So this gets us to a formal definition. Let me now give you a formal definition of, well, not completely formal, a half formal definition of what a zero knowledge proof system or proof protocol is. So a ZKP or zero knowledge proof must have the following properties. Okay, if you have a question in the chat. Okay, so a really good question in the chat is, why don't we just let Victor see that Peggy goes through A and comes out from B? That proves to Victor that Peggy knows the password, right? Because if Victor can see that Peggy goes through A and comes out of B, that's a good enough knowledge, right? And it also doesn't leak the password. But the problem is that we are going to require something much more. Our requirement is not just that Victor shouldn't be able to know anything about the password. Our requirement is that Victor shouldn't have any extra information. Okay, so the only thing that Victor is allowed to figure out is that Peggy knows this password. Now, what happens if we do what you just said? Well, generally, we are, of course, going to later on use this on blockchain and so on. So we assume that Victor can record the whole interaction, right? So, of course, this is just a metaphor. In practice, the way this works is that they're going to send some messages maybe over a blockchain, and Victor can basically record the entire thing. Now, the problem with having Peggy go from one entrance and come out of the other entrance is that if Victor just videotapes this, then Victor can prove to others that Peggy knows the password. And this ability to prove to others the same thing that was proven to you, that's considered knowledge. And we want to have zero knowledge. We want to make sure that Victor really doesn't get any extra information. And I'll get to this really soon in this formal definition. So a zero knowledge proof must have these properties. My first property is that if both Peggy and Victor are honest, and if Peggy really has the knowledge that she claims, so if both Peggy and Victor are honest, and Peggy's claim holds, then Victor would be convinced. Now, of course, this is not 100%. I would say Victor would be convinced with high probability. And what I mean by this is that for any probability P, there is a way of making sure that the probability of Peggy actually being truthful is more than P. So the idea here is that if I just repeat it many times, I can make it so that the probability that Peggy was just really lucky becomes really small, right? So that's my first property that I want to have. The second property is that if Peggy is dishonest, or if Peggy is lying, then she cannot convince Victor. Or actually, to be more specific, she can only convince Victor with a very low probability, a probability that tends to zero. So effectively cannot convince Victor. But these are just the definitions of a proof. The third definition is the most important part. The third part of the definition, or the third property that I need, is that Victor gains no extra knowledge. Apart from the fact that Peggy's claim is actually true. Okay. So the only thing that Victor is allowed to find out is that Peggy's claim is true. So in this case, again, and I'm assuming that Victor can record the entire interaction. If Peggy goes through entrance A and comes out of entrance B, Victor can record this, and this is some extra knowledge. The recording is an extra knowledge that Victor has, because he can then take that recording and show it to someone else and prove to them that Peggy knows the password. But we don't want that. We just want to convince Victor that Peggy knows the password, and we don't want Victor to get any extra abilities out of this. Victor shouldn't be able to convince someone else. Okay. So actually, this is called the zero knowledge property. A really good question is, how can you show if a particular protocol has the zero knowledge property? Right? Because in these cases, I just claimed that it has the zero knowledge property, but how can I actually show it? How can I prove that a protocol has the zero knowledge property? How can I prove that Victor cannot get any extra information? Now, one way to prove the zero knowledge property, and actually the classical way of proving zero knowledge property, is based on this very simple observation. So suppose that Victor records the entire protocol, okay? So imagine that Victor records all the interactions. And let's say he then plays this recording for someone else, okay? And later plays the recording for, I don't know, let's just give another name to someone else. Let's say Sarah. Then from Sarah's point of view, the recording should look fake. So there should be no way to convince Sarah that the recording is not fake. No way to convince Sarah that the recording was not staged. And of course, we're not just talking about video here, we're talking about a digital recording as well. So you can imagine that maybe Victor and Peggy were actually interacting over a blockchain. So maybe everything that they did was recorded in a smart contract. And then we're showing the smart contract and all the interactions with the smart contract to Sarah. And then from Sarah's point of view, it should all look fake. Now, what do I mean by this? Let's just look at these two examples. Yeah, let's actually look at the first example. So suppose that you're Sarah and Victor comes to you and says, hey, Peggy knows the colors of these two balls, and I've made a recording. And of course, because the recording is made by Victor, the recording is also colorblind. And he shows you that here's the entire recording. You can see that whenever I swap the balls, Peggy can figure out that I've swapped the balls, and whenever I don't swap the balls, Peggy figures that out as well. So you should also be convinced that Peggy knows the colors of these balls. Of course, if you're Sarah, you would just accuse Victor and Peggy of staging the whole thing together, right? So maybe Victor and Peggy are just colluding with each other, and maybe it's not really random. Maybe Peggy actually knows whether Victor is going to swap or not, and the whole thing is just a fake recording. or in this example, suppose that Victor shows again a recording to Sarah, and Sarah sees that Peggy goes inside the cave. And basically, again, when I say recording, I mean a recording of everything that Victor could see. So Sarah sees that Peggy goes inside the cave, and then Victor says which entrance she has to exit, and Peggy always exits from the right place. Again, this will not convince Sarah of anything, right? Because from Sarah's point of view, maybe they had a sequence of A's and B's that both Peggy and Victor knew beforehand, and maybe Peggy doesn't actually know this password. It's just that she's going according to that predefined sequence, and Victor is also calling that predefined sequence. Whereas if we do what you mentioned in the chat, if we actually give a recording to Sarah that shows that Peggy went through A and came out of B, then Sarah would be convinced, right? So that would be some extra information that Victor has, and that's not allowed. So generally, the way that we show we have zero knowledge property, the zero knowledge property is by showing that if Victor replays a recording of the entire thing for someone else, it wouldn't be convincing to them. It wouldn't convince them of anything. And the way we say it wouldn't convince them of anything is that they can just imagine that this was a collusion and like Victor created the entire thing on his own. Okay. So, but let's get out of metaphors and let's get into some actual computer science. Let's see an example. So here's my first real example, and this is an example that we had actually in our homeworks. So imagine that everyone knows a very big prime number. So let's say everyone knows a big prime number P, and they also know a primitive root G modulo P. And let's say that Peggy claims that she also knows, okay, let me do this like this. So everyone knows P, G, and let's say some number X, and all of our calculations are modulo P. And Peggy claims that she also knows the discrete logarithm of X. So Peggy claims she knows a particular value Y such that G to the power of Y is congruent to X modulo P. And again, this was in the homework, if you remember, and this P is a large prime number. And this G is a primitive root. Okay. Now, how can Peggy prove this to Victor? The simplest way would be to just disclose Y, but that's going to give some extra information to Victor. The only thing that Victor should figure out is that Peggy knows Y, but Victor should not know anything about Y or anything else. So the only thing that is going to be added to the knowledge of Victor is that Peggy knows a Y that satisfies these conditions. Okay. Now, we saw kind of a solution last time. So this was the first solution. And this was very much similar to El-Gamal encryption. So we had a situation like this. Let's say I have Peggy here. And I have Victor here. And there are some things that are public. So everyone knows P, G, and X. Okay. And then Peggy knows Y. She knows a Y such that G to the power of Y is X. Okay, so that's Peggy's secret. And she wants to prove this to Victor. Now, what we are going to do is something very similar to Diffie-Hellman key exchange, or basically El-Gamal encryption. Remember, if we had a situation like this in El-Gamal, this Y was supposed to be Peggy's secret key. And then Victor could actually send messages to Peggy, right? And then only Peggy could decrypt those messages. So the way this worked was that Victor chose some other secret, let's call this Y prime. And then, well, he just defined X prime, let's put it here, X prime to be G to the power of Y prime. Okay, and he also chose a message M. And what did he send to Peggy in El-Gamal? Well, we want to first do the Diffie-Hellman key exchange. So he would send X to the power of Y prime, right? And he would also send M plus, so here basically X to the power of Y prime. Oops, sorry. I'm completely lost here for a second. Sorry, he would send X prime, and he would send the message M plus X to the power of Y prime. Right. So here the idea was that if you do the calculation, X to the power of Y prime is basically G to the power of Y to the power of Y prime, which is G to the power of Y prime, right? And it's also equal to X prime to the power of Y, because X prime to the power of Y is G to the power of Y prime to the power of Y, which is G to the power of Y prime. So if Victor sends X prime to Peggy, then Peggy can raise this X prime to the power of Y, assuming that Peggy knows Y, and she can find G to the power of Y prime. And this G to the power of Y prime was the shared secret between Peggy and Victor, right? This is the shared secret, or, okay. And then he could use this shared secret to basically encrypt a message. So in order to send a message M to Peggy, he would just add this shared secret to M. And then because Peggy could find this shared secret, she could also find them. That's what El-Gamal encryption was basically. Now, how can I change this so that Peggy can prove to Victor that she knows Y? Well, the only person who can actually do decryption here is someone who knows Y. So if Victor chooses a value of M uniformly at random, and then encrypts it and sends it to Peggy, and then if Peggy sends the correct value of M back, so basically what's happening here is that Victor is encrypting a randomly chosen message M, sending it to Peggy, and Peggy is decrypting that message successfully and sending the decrypted message back to Victor. If she can do this, then Victor would be actually convinced that Peggy knows Y. Because only someone who knows Y, only someone who knows Peggy's secret key can do this decryption, because the encryption was done using Peggy's public key. Okay? And of course, they can just repeat this. So Victor can just keep giving different values of M, of course, in encrypted form. And if Peggy can decrypt them, it means that Peggy actually knows this value of Y. Okay, so that's one solution. Now, why is this zero knowledge? You know, the other two properties are easy. So if you look at these two properties, of course, if both Peggy and Victor are honest and Peggy really knows this value of y, Victor will be convinced. And also, if Peggy doesn't know this value of y, it's impossible for her to convince Victor. Of course, we have some very small probability that she just gets lucky, but the way we avoid that is by just repeating the protocol many times. But why do we have the zero knowledge property? Why is it that Victor doesn't get any extra information? Now, intuitively, you can see here that every time the interaction that's happening is that Victor is choosing some value of M, encrypting it and sending it to Peggy. And Peggy is decrypting the same value of M and sending it back to Victor. So intuitively, it's clear that Victor is just getting the same value that he sent. So nothing is added to Victor's knowledge. Victor knew M beforehand, and he's now receiving M again. Okay. But let's look at this kind of proof. Let's say that Victor somehow makes a recording of the entire interaction and then shows this recording to someone else. So shows this recording to Sarah. What does Sarah see? She sees that Victor is just sending some messages M to Peggy, and Peggy is sending back the same messages, right? Of course, Victor is sending them in an encrypted form, and Peggy is sending them back in the decrypted form. But again, from Sarah's point of view, maybe Victor is faking the entire thing. Maybe Victor has somehow told Peggy about the sequence of messages M that she's going to receive. And then every time when Victor is sending this encrypted message, Peggy is not really decrypting it. It's just that she already knows M because she's colluding with Victor. So maybe Victor just faked the entire recording. Okay, so my point is that this kind of protocol convinces Victor, but Victor cannot use it to convince someone else. And that's one of the main properties in zero knowledge. But here's another solution. So solution number 2. And okay, first of all, why would I not like solution number 1? I wouldn't like it, especially in cases where the decryption is going to be the same as the signature, right? So it doesn't happen in El-Gamal, but if I had RSA here, and if I wanted to prove that I have a particular RSA secret key, so let's say I'm Peggy, we have an RSA public key, and I claim that I have the corresponding secret key. Now, if we do something like this, every time that I'm decrypting using my RSA key, I'm basically also giving you a signature. So you might be able to use that signature later on. So that's why I might not like something like this. But with El-Gamal, I don't have that problem at all. Okay, let's talk about the other solution that I can have. So as Peggy, I'm claiming that I know a particular value of y such that g to the power of y is equal to x modulo p. And again, here everyone knows g, x, and p. The secret is y, and only Peggy knows y. Okay, so here's the second protocol that I can come up with. So in step 1, Peggy just chooses a random number r, chooses a random number r, and let's say she computes s, which is g to the power of r. Okay. And she just sends this s to Victor. Now, Victor has two choices. Okay, sorry. I'm blanking on this. What's it? Okay, sorry. So let's do this again. So she knows g to the power of y is x. So let's say Peggy chooses a random number r and computes g to the power of y plus r and sends it to Victor. Okay. Now, in step 2, Victor has a choice. Victor can ask for either r or y plus r. Okay, so Victor just tells Peggy, tell me r, or tell me y plus r. Now, and okay, so step 3 is that Peggy gives the information to Victor. So Peggy answers. And then in step 4, Victor can verify this. Okay, so given r, so if he asked for r and Peggy gave him r, Victor can compute x times g to the power of r and check if this is equal to the value that was given to him. So maybe let's give this value a name. Let's call this capital A. Okay. So Peggy gave capital A to Victor. Now Victor knows A, which is g to the power of y plus r. Okay, remember y itself is the secret. Now in the next step, Victor can ask for either y plus r, or he can ask for r itself. If he asks for r and Peggy gives him r, he can verify the value of r, because he can take r and compute g to the power of r, multiply that by x, and basically check that this is equal to a, right? Because x is g to the power of y, so x times g to the power of r should be a, should be g to the power of y plus r. Okay, and on the other hand, if given y plus r, Victor can also compute it, right? Victor can just raise g to the power of y plus r and check that the value a that was given to him by Peggy is actually really g to the power of y plus r. Okay. Now, why does this prove anything to Victor? First of all, let's talk about why this doesn't really leak much information intuitively. So Peggy is choosing a random number r each time, and then Victor is either asking for r or y plus r. But both of these are going to be random, right? So if I'm Peggy, I'm happy with disclosing r, because if I disclose r to Victor, I'm just disclosing a random number that's not going to give him any extra information. And the same thing for y plus r. And now to be more specific, this is not necessarily just y plus r. This is y plus r modulo p minus 1, right? So if I give him y plus r, this is also going to look exactly random because r was chosen randomly. So y plus r is not leaking any information about y because r was chosen uniformly at random. Okay, so I don't have an information leak. But why is it that only someone who knows y can do this? Okay, so if you know y, you can compute g to the power of y plus r. And then if I ask you for r, of course, you know r, you can answer. If I ask you for y plus r, since you know r and you know y, you can also answer that. So if Peggy is actually telling the truth, and if she actually knows y, she can always give values here that will pass this check. But what happens if she doesn't know y? If she doesn't know y, then she's generating some value a, and maybe she knows what the discrete log of a is. So maybe if I ask her for r, she can answer that. But then if I ask her for y plus r, that would not work here, right? And the really important point is that Peggy doesn't know what Victor will ask. So Victor is asking, let's say, uniformly at random. And because Peggy doesn't know what Victor will ask, Peggy cannot anticipate what she has to answer. And the only way that she can answer both types of queries is if she knows why. Now, again, we have a situation where maybe Peggy gets lucky and she can answer some of the queries, but if we just keep repeating this, the probability that Peggy gets lucky in every iteration tends to 0. So at some point, Victor will be sufficiently convinced that, okay, Peggy is not lying. Peggy really knows why. Okay. So this was our first example, where we just wanted to show that we know a discrete log, and we had 2 different solutions here. You can also read the Wikipedia article on zero-knowledge proofs, and it gives you an even more detailed analysis. So Wikipedia is generally great in this field. But now let's see what else we can find zero-knowledge proofs for. So I'm going to change my problem a little bit. Well, not just a little bit, a lot. So this is the next problem I want to consider. Let's say that I have a graph. So let's say there is a graph G. And we're assuming that this G is public again. So both Peggy and Victor know about G. And here's Peggy's claim. Peggy claims that she knows a Hamiltonian cycle in G. And remember, in a graph, a Hamiltonian cycle is a cycle that sees each one of the vertices exactly once. And actually finding a Hamiltonian cycle is an NP-complete problem. So if this graph G is really large, if you can imagine that this graph G has maybe millions of vertices and edges, it's basically an impossible problem to really compute this, to compute a Hamiltonian cycle. So Peggy is claiming that she knows a Hamiltonian cycle, and she wants to prove to Victor that she knows a Hamiltonian cycle. But again, we want to give a zero-knowledge proof. So we want to make sure that Victor cannot find any extra information, that he can only figure out that Peggy knows the Hamiltonian cycle, but he shouldn't get any extra information. He shouldn't know what the Hamiltonian cycle is, but that's just a very specific type of information. We want to make sure that Victor doesn't get any extra information of any type, okay? So here's how we can do this. So we can say that, well, let me again give you a non-solution first, kind of a non-solution. So I can say in step 1, Peggy just chooses some permutation of the vertices. Okay, so let's say my vertices were numbered from 1 to n. I'm just randomly changing the order of the vertices. Okay, chooses a permutation of vertices. And this gives her another graph. This is the graph H, which is going to be isomorphic to G. Okay. So as Peggy, I'm just taking a random ordering of the vertices. I'm changing the names of my vertices. I'm randomly ordering them. I will get another graph H. This graph is basically the same as G in terms of its shape. It's isomorphic, but the vertices have been reordered. Okay. Now here's step 2. Again, Victor has a choice. Victor can ask Peggy to do one of these two things. The first thing he can ask Peggy to do is to give him the permutation. So he can ask Peggy to prove that this graph H is really isomorphic to G. Oh, and I forgot to say that Peggy actually publishes H and sends H to Victor. Okay. So we had an original graph G. Peggy was claiming that she knows of a Hamiltonian cycle in G. Okay. She reordered the vertices, and this reordering is supposed to kind of disconnect the graph, the current graph from the previous graph. And then this new graph H is publicized. So Victor now knows this new graph H. But then Victor can ask Peggy to do one of these two things. He can ask Peggy to give the permutation, basically to prove that H is isomorphic to G, or he can ask Peggy to give a Hamiltonian cycle in H. Okay. So again, let's say this was my graph G. I want a graph with a Hamiltonian cycle. And okay. Now this is a very small graph, of course, but it does have a Hamiltonian cycle. So let's say my vertices were 1, 2, 3, 4, 5. And my Hamiltonian cycle is 1, 2, 4, 5, 3, right? Now, of course, in practice, this would be a huge graph so that it's not so easy to compute the Hamiltonian cycle. It would be impossible to compute the Hamiltonian cycle because it's an NP-complete problem. And so in the first step, Peggy is just going to change these labels. So maybe Peggy is going to say, I'm going to change these labels to, let's say, 5, 1, 4, 3, 2. Okay. So she will give this new graph to Victor, and Victor sees this new graph. He also knew the previous graph. But there is no way for Victor to really check that this is the same graph and only the numbers of the vertices have changed, especially, again, if this is a big graph. So Victor can ask Peggy to do one of these two things. He can ask Peggy to either give the permutation, so tell me what was the mapping from the old numbers to the new numbers so that I can check that this is the same graph. Or he can ask Peggy to give him a Hamiltonian cycle. So show me that there is a Hamiltonian cycle in this reordered graph that you have right now. And of course, the next steps 3 and 4, is that Peggy does this. Peggy provides the information in either 1 or 2, and Victor verifies it. Okay. Now, again, the crucial point here is that Victor has a choice, and he can choose to ask either one of these questions uniformly at random. So if Peggy is cheating, she doesn't really have a good chance of being able to convince Victor, right? Because how can Peggy cheat? There are basically two cheats that Peggy can do. she can maybe create a graph H that is not isomorphic to G. Maybe she just creates a new graph that looks completely differently, and then she gives that to Victor. But then there is a 50% chance that Victor asks for the permutation. And if that happens, then Peggy would be caught, right? Or the other case that she can do is that, well, she can just say, well, okay, let me see what other things. No, that was the only thing. Yeah, that's basically the way she can cheat. The only way she can cheat is to give a different graph that is not really isomorphic, and then there's a 50% chance that she gets caught. And in the other case, if the graph she gives to Victor is actually isomorphic to G, then she wouldn't be able to give a Hamiltonian cycle unless she knows a Hamiltonian cycle in G. Okay. So, but we have a problem here, and the problem is that we have some leak of information, right? So in order for this to work, we have to repeat this solution many times. And the way we repeat it many times is that every time Peggy is going to create a new graph H, send it to Victor, and Victor is going to ask maybe for the permutation or the Hamiltonian cycle. But the problem this creates is that we are giving Victor a lot of other graphs that are isomorphic to G. And if Victor keeps asking for the Hamiltonian cycle, then he will actually have a lot of graphs that are isomorphic to G, and he will have a Hamiltonian cycle in each one of those. And that's not nothing. That's actually some information, right? And then he might be able to use that information to actually find the Hamiltonian cycle in G. But even if he can't do that, the important point is that we are leaking some information, and that's not allowed. We shouldn't leak any information. Okay. So how do I actually make sure that I'm not leaking any information to Victor here? Well, I'm going to use a commitment scheme. So instead of saying that Peggy chooses a permutation and obtains this graph H and sends H to Victor, I'm going to say that Peggy just commits to the graph H. And the way we commit to a graph is very similar to what we've seen before. We can use a hash-based commitment scheme. So this is the actual solution that I want. And by the way, we don't have any proof that the graph isomorphism problem is a hard problem. So it might be that if Peggy gives a Hamiltonian cycle in H to Victor, then Victor has a way of figuring out the isomorphism between H and G, and that would give him a Hamiltonian cycle in G. So we have that problem as well. So my solution is going to be like this. In step 1, Peggy is going to again choose a permutation of the vertices, and she's going to compute a graph H. And this graph H is going to be isomorphic to G. So again, just like this example, the only thing I'm doing is that I'm changing the numbering on the vertices. Okay. Now, instead of actually giving H, in step 2, Peggy commits to H. And the way she commits to H is that she commits to every edge of H. So what does this mean? This means that if I have an edge E, which is from vertex U to vertex V in H, then I just compute the hash of U, V, and a nonce. And let's say this was my ice edge. So I call this HI and publish HI. And by publish, I just mean give it to Victor. Okay. So I'm not actually giving the graph H to Victor. I'm just giving him the hash of every edge. And this hash also has a nonce in it. Okay. Now, the rest of it is very similar. In step 3, Victor can ask for one of these two things. The first thing he can ask for is to prove the isomorphism. Okay. And the second thing he can ask for is a Hamiltonian cycle in H. Now, if he asks me to prove the isomorphism in step 4, as Peggy, if Victor asked for 1, I'm going to open all of the commitments. So I'm going to show him the entire graph H. And I'm also going to show him the isomorphism, the permutation that I applied on the vertices. Okay. So Peggy discloses or reveals every edge in H and the permutation. Otherwise, if Victor asked for 2, so if he asked to see a Hamiltonian cycle in the second graph H, then Peggy will only show that Hamiltonian cycle. Okay? Peggy only reveals the edges that are in the Hamiltonian cycle. Now, what does this achieve? Basically, we are not leaking any information now, right? Let's look at the information that Victor can get. If Victor asks to prove isomorphism to him, we are just giving him the graph H, and this graph H was chosen randomly, right? Peggy chose a random permutation. Whenever I say chooses, I mean choosing uniformly at random. So Peggy is choosing a random way of permutating the vertices, and that's how she's computing the graph H. So if Victor asks for a proof of isomorphism and Peggy reveals everything in H, the only thing that Peggy is giving to Victor is like a random ordering of the vertices. And that's not any kind of information that is usable at all, right? But what happens if Victor asks for a Hamiltonian cycle? Then he's just, again, getting only a cycle, but this cycle is also in a randomly ordered graph. So he's just going to get a random permutation of the numbers from 1 to n. He's not going to get any kind of information. So we're not leaking anything. Whereas here, previously, when I didn't have this kind of commitment scheme, if he asked for the Hamiltonian cycle, he got a Hamiltonian cycle, and he also knew the graph in which the Hamiltonian cycle was located. And this graph was isomorphic to the original graph, so that was some extra information that Victor was getting. Whereas here, when he's asking for the Hamiltonian cycle, he's basically just getting a random ordering of the vertices from 1 to n. And this is the thing that makes sure it's a zero knowledge proof. Now, again, you can verify that Peggy can do all of this only if she actually knows a Hamiltonian cycle. If she doesn't know a Hamiltonian cycle, she has to either cheat in this part so that she gives a graph that is not isomorphic, in which case there is a 50% chance that she gets caught, or she doesn't know the Hamiltonian cycle, so there is a 50% chance that, again, she gets caught because Victor can ask for the Hamiltonian cycle. And if we just repeat this many times, Victor will be convinced with very high probability that Peggy knows the Hamiltonian cycle. To be more specific, if I do this protocol n times, the probability that Peggy can successfully do it without knowing the Hamiltonian cycle is 1 over 2 to the power of n. And 1 over 2 to the power of n tends to 0 really fast when n tends to infinity. So in practice, if you do this 100 times and she can do it in 100 times, she knows the Hamiltonian cycle. You can be pretty sure about that. Okay. So these were some examples. Let me just do another example. I will probably run out of time. If I ran out of time, you can leave at 10:20. I will just put the recording on Canvas and you can watch it later. So this is the other example. Let's do 3 coloring. So let's say that we have a huge graph. And let's call this graph G. And let's say that Peggy claims that she knows a 3 coloring of G. So she knows a way of coloring the vertices of the graph G with 3 colors, let's say red, green, and blue, such that no 2 neighboring vertices are the same color. Okay. So she wants to prove this claim, but of course she doesn't want to show the coloring. She wants to give a zero knowledge proof. How can she give a zero knowledge proof of this claim to Victor? So let's say I have my graph. And again, I'm going to draw a very small graph here. But in practice, this would be a huge graph, right? So let's say this is my graph. So again, what I'm going to do is to use a commitment scheme, a hash-based commitment scheme. How do I do this? Let's say that my vertices have numbers 1, 2, 3, 4, 5, and 6. Now, in step 1, Peggy is just going to choose a coloring. So Peggy chooses a coloring of G. And commits to it. Okay. So how do you commit to a coloring? Well, for example, if vertex 5 is green, she computes hash 5, which is the hash of the number 5, and let's say the color green and a nonce, and publishes this H5. Okay, so the role of this commitment is that she is committing to a coloring of the graph. No one else can see the coloring, but she cannot change the colors that she has assigned to each one of the vertices because she has published the hash of those colors and vertices. Okay, so let's say, for example, this one was red, this one is green, this one is blue, and the other vertices are also colored. Now, in step 2, again, we have to give a choice to Victor. So Victor chooses 2 neighboring vertices, and he can choose this as he likes. So let's assume that he chooses also at random. And then finally, in step 3, Peggy is going to show us the colors of these two vertices. So Peggy, so let's say the two neighboring vertices were U and V. Peggy reveals the colors of U and V. Okay. Now, first of all, why is this convincing? Why is it convincing to Victor? Well, Victor cannot see the entire coloring, but he can basically randomly choose two neighbors, and then Peggy has to reveal the colors of those two neighbors. And we know that this was a commitment scheme, so we know that Peggy could not change the colors after she committed to them. So if Peggy is lying and she doesn't actually know a coloring, she will eventually get caught, right? So more specifically, if I have M edges, and if I choose an edge from these M edges randomly here and choose the two vertices on the two sides, there is at least a 1/m probability that Peggy gets caught if she doesn't have a valid coloring. So if I just repeat this process many times, and if Peggy can always give me colors that are different for any two neighboring vertices that I choose, I would be convinced that Peggy actually knows a coloring. But of course, the problem is, does this really leak any information about the coloring? Now, here's the part where things get interesting. So if Peggy knows a coloring, she knows a way of coloring this graph with three colors, right? And we can easily assume that this graph cannot be colored with two colors, because the only graphs that can be colored by two colors are bipartite graphs, and it's easy to check if a graph is bipartite. So if the graph is bipartite, there is no secret, okay? So Peggy knows a way of coloring this graph with exactly three colors. But if she knows one way, she knows at least 6 ways of doing this coloring, right? Because I can change the order of my colors. I can do any permutation on my colors. I can change all of the reds to blue, all of the blues to green, all of the greens to red, right? So actually here, when I say Peggy chooses a coloring, I know that she has at least 6 choices, okay? So she chooses a coloring. Let's say she does it uniformly at random from her 6 choices. And this is 6 because 3 factorial is 6, right? So the number of ways I can permutate my colors is 6. Now, if she does this, every time that Victor is asking for 2 neighboring vertices, what kind of information is Victor actually getting, right? So take 2 vertices, take U and V, okay? And their neighbors. Peggy is choosing one of the 6 choices uniformly at random. So what is the probability that U is green? It's 1/3. What is the probability that it's blue? It's 1/3. What's the probability that it's red? It's 1/3. The same for V. So from the point of view of someone who can only see U and V, it's as if these vertices are colored randomly. It's just that they're getting different colors. So every combination of colors is equally likely. Every combination of different colors is equally likely. So the information that Victor is getting here is basically just random information. He's getting colors for U and V that are not distinguishable from random. And the entire point of it, the reason that this works, is because we had this commitment scheme here. So when he asks for the colors of U and V, he doesn't know anything about the colors of the rest of the graph. So his viewpoint is limited to the vertices U and V, to these 2 vertices. But any 2 vertices look random because Peggy chose one of the 6 possible colorings uniformly at random. Okay. And of course, again, if we continue this for many iterations, Victor will be convinced. We have to add some extra conditions, like you cannot have too many iterations. It shouldn't be that Victor can ask the color of every vertex many times. Maybe we can just add a constraint that you cannot reuse your vertices, or you cannot ask for the same pair of vertices more than a fixed number of times. But anyway, the important point here is that we're not leaking any information, and Victor is actually convinced that Peggy knows a coloring. But the other really interesting thing here is that Victor cannot prove this to someone else, right? So again, if Victor just records the entire interaction, and then if he shows this interaction to someone else, to Sarah, Sarah will not be convinced, because maybe Victor was just faking the entire thing. Maybe Victor was collaborating or colluding with Peggy, and every time Peggy knew which vertices U and V Victor is going to choose, and so Peggy didn't really have a coloring of the entire graph. She just had a coloring that gave different colors to U and V. So you see, this is convincing to Victor, but it's not convincing to someone else. It's not like Victor can take this and prove to someone else that he didn't fake the entire thing. And because whatever Victor shows to someone else can be accused of being entirely faked by Victor himself, then this is definitely a zero knowledge proof. So Victor is not getting any extra information. Okay, that's all for today. In the next session, we will talk about more practical zero knowledge proofs. And if you have any questions, please ask in the chat. Okay, we have a great question in the chat. I'm very happy you asked this. Can a signature be considered a zero knowledge proof? Because it proves that you know the private key without revealing it. No. So again, in order for it to be a zero knowledge proof, it shouldn't give any extra information, right? The only thing that so let's do this. Let's say that I'm Peggy. So I have Peggy here, and I have Victor here, and Peggy has a secret key, SK. And she wants to prove to Victor that she has this SK. And there is, of course, a corresponding public key, PK, that everyone knows. Now, of course, one way you can prove this, and this was actually also in the homeworks, is that Victor can just choose some message M, and he can send this message M to Peggy. And if Peggy can send a signature on M using her secret key, and if this is a valid signature, then Victor would be convinced that Peggy has the secret key, right? But this is not zero knowledge. It's not zero knowledge because Victor now knows something more than the fact that Peggy knows SK, right? Victor also knows the signature on M. So this is some extra knowledge. This is something that Victor didn't know before. The whole point of a zero knowledge proof is that Victor should be convinced that Peggy knows SK, but Victor should not get any extra information. This signature is actually extra information. This is something that Victor could not have made on his own, right? So another way of looking at this is that if Victor records this interaction and then shows this to Sarah, would this be convincing to Sarah? Can Sarah say that Victor faked the entire thing on his own? No, Sarah cannot say that Victor faked the entire thing on his own because Victor didn't know the secret key. And if Victor didn't know the secret key, he couldn't come up with a valid signature. So the existence of this valid signature means that someone in here, presumably Peggy, knew the secret key. And so the entire thing was not fake. Yeah, it's a very subtle issue. You have to make sure there is no information other than the fact that Peggy knows SK that goes from Peggy to Victor. And this is extra information now. But a very nice point here is that we can sometimes use zero knowledge proofs in place of signatures, and we might see some examples of this if we have time. So for example, let's say you want to sign into your email account. How can you sign into your email account? The worst way you can sign in is by sending your password, right? So you can send your password to Gmail and they can check if it's the same password that they have on file, and if so, they can give you access. But it would be much better if you do it with a signature. It would be much better if you have a secret key and a public key, and let's say Gmail knows your public key, the public key corresponding to your account, and they just send you a challenge. They send you some value M, and you sign it and send it back, and this proves to them that you know the secret key, and then they give you access. But it would be even better if they could ask for a zero knowledge proof. So if you could give a zero knowledge proof to Gmail that I actually own this account and I should have access to my emails, that would be much better, because then Gmail cannot fake that and cannot get any extra information from that, cannot even get your signature. So yeah, that's a nice thing. So someone is asking two-factor authorization. Not really, it's not exactly the same thing, right? Because two-factor authorization, it also depends on a lot of hardware. So if we want to really solve this problem on the software side, I want to make sure that whatever I'm sending you is something that only you can have access to. But in a sense, you can look at two-factor authorization as something similar to this case, right? So the point here when we were using El Gamal zero knowledge was that Victor was sending a message to Peggy, and only Peggy could replay this message back to Victor, right? So that's also the idea behind two-factor authorization. If you get, for example, a text message, the idea is that only you can receive that text message. So if it contains some number M and then you can give that number M back, that proves that you were the intended recipient. But the problem is, in that system, like, it's not really only you who can read the message. Of course, your mobile phone operator can also read it. So it's not really the same thing, but kind of the same idea.